Hello and welcome to today's webinar. Today we're going to be looking at little known but certainly useful system registers. Let's get started. Let's look at our agenda for today. We'll start by looking at what system registers are. We'll discuss the difference between bit-type system registers and word-type system registers, and based on our topic today, we'll look at those that are overlooked, which might be useful in your program. There'll be demonstrations throughout, and we'll finish with a Q&A session. System registers are predefined OCS variables with specific meanings related to system status or other embedded parameters in the OCS. They are typically read-only, but can also be written to adjust system settings or perform useful functions. There are two different types of system registers: bit type, %s, and word type, %sor. System bits are limited, as there are only 13, whereas system registers are more numerous, with up to 222, divided between standard system registers and extended system registers. System register support varies by each OCS model and by which logic language you use. A detailed system register table can be found in the user's manual for each OCS model. Let's look at the 13 most commonly used system bits. These are read-only, and the first one, %s1, is on for the first scan of the logic and then off afterwards. We frequently use it to set initial variable values. %s7 is always on, and %s8 is always off. We use these often, especially S7, when starting a rung with only a function block. Other useful system bits include those representing pulses. We have %s3 for a 10 millisecond period, %s4 for a 100 millisecond period, and %s5 for a 1 second period. Each of these system bits is on for the first 50% of the period and off for the second 50% of the period. %s5 with its 1 second pulse can be particularly useful as a flash bit. Customers often use it periodically for that function. Now, the vast majority of system registers are of the word type, ranging from SOR1 to SOR222. We'll focus on these for our discussion today. Unlike S bits, which are read-only, SOR bits can be a mix of read-only and read-write. The read-write ones can be written from logic, the screen, or both. The user manual and the help file provide details on which SOR types can be written to and from which source. Now we'll look at some of the essential system registers, beginning with SOR3. SOR3 indicates the current displayed system screen. SOR1 and SOR2 are not overlooked. SOR1 contains the user screen number displaying the current screen chosen by the user. SOR2 is the alarm screen number, showing the screen displayed when forced from logic using a D-type coil. Now SOR3 differs as it displays the value of the current system screen when there is one displayed. If the customer accesses the system menu, the value in SOR3 indicates the specific system menu screen they are on. As application designers, we can write to SOR3 to force a particular system menu screen to be displayed, creating shortcuts for users to navigate directly to specific functions like changing the time and date. It's especially useful for setting the time and date, making it the most practical option. So now we'll proceed to demonstrate this feature. So here we have a screen displaying the date and the time. There's a push button that allows us to jump to the system menu screen where the clock is set. When we press this button, we'll see ourselves in the system menu without manually selecting it. Now we'll go ahead and make a change, adjusting the time. When we press Escape, we'll return to the original screen. This capability lets users jump to a particular screen on the system menu and quickly return to where they were before. We can also manually set the value of %S or 3 to a number between 1 and 24, representing the various system screens. By manipulating %S or 3, we can jump to any system menu screen we desire. Now we'll explain how the jump button works. When pressed, it triggers logic in the program, copying the value of 10 into %S or 3, which corresponds to the time and date screen. We can see this process in Cscape, where the push button action writes the value of 10 to the screen variable mapped to %S or 3. It offers an efficient way to navigate within the system menu. System registers 35 and 36 provide a unique serial number for each OCS. When read together as a double integer, you get a guaranteed unique number. They represent the changeable or unique parts of the Ethernet MAC ID, which is required for every Ethernet device. Our fixed prefix, 0, is not unique and not included in the system registers. By examining %S or 35 as an unsigned double integer, you get 32 bits of uniqueness, whether displayed in hex or decimal. These registers are valuable for various purposes, such as verifying the machine's serial number against a target to prevent unauthorized duplication. Additionally, they can reconstruct the MAC address for display on the screen or other functions. In summary, System Registers 35 and 36 offer a way to obtain a unique serial number for each OCS, serving multiple functions, including security assurance and MAC address reconstruction. Now we'll look at the practical use of %S or 35 and 36. First, we observe S or 35 as a 32-bit value in both hex and decimal formats. This unique value is specific to this XL7 OCS, ensuring uniqueness for each unit. To reconstruct the MAC address, we combine the fixed prefix 00E0 with S or 36 and S or 35 in hex, creating the Ethernet MAC address. Now let's see how we can leverage the serial number's uniqueness as a machine builder. We can create a logic algorithm that processes the serial number through a math function, generating a unique authorization code. During deployment, the operator enters this code manually. If the entered code matches the expected code based on the serial number algorithm, the machine is effectively authorized to operate. Otherwise, appropriate action can be taken, such as preventing operation and displaying contact information for support. Now we'll look at the logic in Cscape to understand how this works. If the serial number does not match the authorization number, we force the authorization error screen to appear. In a real application, the logic would be more sophisticated and we would use OEM features to hide the details of the algorithm. To exit the demonstration mode and return to normal operation, we've included a fixed button on the bench. In conclusion, this demonstration illustrates the potential use of serial number system registers, particularly SOR35 as a double integer, to implement an authorization system in your machine logic, enhancing security and control. However, we must always use such features responsibly and ensure compliance with all applicable laws. The last overlooked system registers that we'll look at today are SOR171 and SOR172, which provide touch coordinates on the screen. SOR171 contains the x-axis coordinates and SOR172 contains the y-axis coordinates for the latest place touched by the user. When creating objects in Cscape and placing them on the screen, the lower left-hand corner of the object its x and y coordinates. During runtime, when the operator touches the screen, the touch location is determined by the x and y coordinates where the finger makes contact. These system registers have multiple uses. By monitoring SOR171 and SOR172, we can tell if the operator is currently touching the screen based on whether both registers are 0, not touching, or non-zero, touching. Additionally, these touch coordinates can be used to activate specific functions when the operator interacts with the screen. Instead of using hidden or non-visible push buttons, we can use touch coordinates to trigger actions such as screen jumps or activating specific bits. So now we'll go back to the bench and demonstrate how touch coordinates can be used in an application. So here we press the screen and you can see as we press it in different locations, we're going to get different values on the x and y coordinate. So that's pretty useful for knowing precisely where on the screen an operator is pressing. Now we've drawn a target here in the middle, and if we press anywhere in this target area, we have ladder logic which is watching for that. So now we'll see what will happen when we do. So we press in there and then we switch to a screen. So we used the x and y coordinates like a jump button. And then we go back to the home screen and then back to the touch coordinate screen. Again, nothing happens when we're touching out here, but when we touch in the target area, because it matches a range of values that we're looking for, we can use it like a jump button. Now we'll look in Cscape and see how that was accomplished. So it's really some simple logic that says, for example, in this case, our x coordinate is between 368 and 496, and our y coordinate is between 207 and 335. Then we're going to switch to screen number 6. So that's really what there was to it, to utilize the x and y coordinates to cause the screen to switch. Now the way to ensure that this works in variable-based logic is to make sure that we've allocated appropriate system registers. In this case, 171 is the x coordinate and 172 is the y coordinate. So in variable-based advanced ladder or in IEC, make sure as you create these variables that you map them to an appropriate system register locations for them to operate properly. And in the case of our earlier demonstration of the unique serial number of capabilities, we have created a variable called MAC-low, which is tied to SOR35. So that's the low word of the MAC address. And we have created a variable called MAC-mid, which is tied to SOR36, which will give you the middle value of the MAC address. and then the high value is just a constant. This is always the same regardless of which OCS you have. So this will give you an idea of how you can map these system register locations to your variables in variable-based advanced ladder, and it works the same way in IEC. So system registers %s and %sor are predefined registers that provide system information. They're usually read-only, but some of them can be written to, and that can make them pretty useful. Most of those we looked at today were writable system registers, except for the touch coordinates, which were read-only. Keep in mind that the best information for system registers is inside the help file in Cscape or in the user's manual. And we covered several of those little known but useful system registers today, including those that allow you to jump to specific screens in the system menu, show where the operator is touching the screen, and revealing the unique serial number, which is part of the MAC ID for each individual OCS. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.